Good morning, good afternoon, good evening, everyone. Thank you for giving me the opportunity to speak in front of this esteemed audience. What I am going to try to do today is to bring across what we, as a small dedicated team in Dolby, are working on building out a test environment to enable us to realistically test the limits of our Dolby.io developer platform as we aim to scale our supported conferencing and live streaming capacity to much higher numbers. My talk today is composed of three main chapters. Chapter 1, here we will provide an overview of what our current supported conferencing capacity is and where we aim to get to in the future. Chapter 2, we take a brief look here into the aspects that we cover as part of our load and scale testing scenarios. We'll take a brief look into the current tool mix we use and why that wasn't enough to meet our needs. Chapter 3, here we will dive deeper into the higher level architecture of the environment that we are currently building, look into some of the key components of that architecture that we believe will help us scale better and build higher testing capacity. And I hereby try to bring across learnings we had and some of the caveats we ran into as we build into this environment. So without much further ado, let's dive into chapter 1. So what exactly is Dolby.io? Maybe for those who don't know, here are a couple of sentences about it. It's an API platform that offers APIs for the integration of high fidelity audio and video solutions into real-time communications, streaming, and media applications. So diving into what the supported conference capacity is. So the Dolby.io platform today supports up to 50 users in a typical conferencing scenario, with the possibility to stream conferences and events up to 100,000 listeners at sub-second latency. So a user typically is someone who actively sends audio and video into the conference, and a listener is typically someone who only receives streams. So it's kind of, you could think of it as a passive participant in a conference. So we are currently working on optimizing various aspects of the platform in order to enable us to scale the number of listeners we support up to 1 million. Additionally, using intelligent video forwarding techniques, we will be in a position to also stream up to 25 presenters within an event to all the listeners that are partaking in that event. Thirdly, live performance streaming is another significant aspect of the platform we are continuing to build out, and as a result, in the near to short term, we do expect an increased amount of traffic hitting our platform. It is thus of paramount importance for us as a scale testing team to be able to build capabilities to assess the reliability and the resiliency of the platform at our supported scale numbers. This has basically led us to embark on a journey to build an environment in-house that would enable us to meet these goals and be in a position mainly to detect issues regarding performance at scale early on in the development process. Achieving that goal additionally in a cost-efficient manner is another significant factor that has played a role in us taking this journey. So moving on to chapter 2 here. So what are our scale testing goals? On the one hand, the goal of this team is to be able to build tools that give engineers the capacity to generate various traffic patterns onto the platform, and this allows them to simulate realistic production side traffic patterns that we're seeing on our platform. At the same time, building a more holistic environment gives us the capability to assess the scale and the reliability and resiliency of the various components of the platform at scale. And this plays a vital role as well in understanding what kind of bottlenecks we might have buried under different types of load conditions. So in this section, we'll look a little bit into some of the key performance indicators we look at and we want to look at holistically as part of the whole platform under different traffic patterns. So the aspects of the system we test for scale can be roughly divided into three categories. We have the signaling infrastructure, we have the conferencing infrastructure, and we have the mixing and streaming infrastructure. In order to understand KPIs at scale for these three sections, we've roughly divided them into six aspects that we cover. Number one is the authentication and signaling establishment. Here we mainly look at how many concurrent authentication and session establishment requests we can handle per second. So at what rate can we handle those? How does a WebSocket infrastructure scale within a geo and across geo? The second aspect is call signaling performance. Here we look at the maximum number of conference creation requests we can handle and at what rate. So how many join conference requests we can handle and how how these aspects actually vary when we have different kinds of loads on the back end. Thirdly, we also have this media arrival rate and also event handling under load. So it's important to understand are participants within the conference receiving the expected media within the expected time frame. Media distribution performance is the third aspect. So under duress, how does the backend actually handle all these different kinds of streams that are flowing in the conference? You have screen shares, you have videos, you have calls, you have chats. So how does all of this work together when we have a mixed set of loads that are running on the system? Audio video specific telemetry and metrics at scale also plays a significant role here. Server-side metrics, so dealing with signaling and routing under duress is something we need to understand in great detail. Number four, which is the load distribution. So when we have varied kinds of conferences happening on our backend, how does the backend scale up and down under these different load changes? And how do they actually shift conferences to be able to avoid any particular server from overloading? The mixing performance is a fifth aspect. Here we deal with a specific component that gives us the capability to record and stream out these different kind of views of the event to a huge audience. So how does this particular component function at scale plays a significant role. And lastly, point number six, we as a team would like to build a holistic collection of metrics that spans the backend, basically the server-side metrics and also the client-side metrics, and be in a position to build a baseline of performance as we add features onto the system. So this gives us a capability to address any kind of regression issues that we're seeing as we bring new features on. And lastly, such an environment allows us to further improve on giving us capabilities to actually run game days or run chaos engineering scenarios and things like that, with the main aim of improving the reliability of the system. So how does our current setup look like? Today, to a large extent, we rely on two sets of tools. It's an in-house set of scripts that essentially run on AWS EC2 instances. And the second aspect is a commercial tool, TestRTC, for a very specific dedicated set of tests. The in-house tools are Python-based. They are based on a fork of AIORTC, which does all the low-level WebRTC, signaling, handling, all that protocol level. And then there's a fork of Locus that's kind of plugged together with that. And this fork of Locus enables us to distribute these jobs across those EC2 instances. The Locus workers are basically simulated clients today, so we do not have any real clients running as part of our internal test scripts. And as such, a test engineer needs to understand what these clients can consume in terms of resources before actually spinning up a certain number of EC2 instances on which to run them on. And this makes it a bit complicated to use for an end user. And this is something we want to address within our new environment. The other aspect is with this approach, we do not really make use of any of the auto scaling, efficient resource usage, monitoring, and these kind of capabilities that actually come out of the box from many of the open source tools like Kubernetes and all the surrounding components that brings with it actually. So we unfortunately do not have fine granular control of that today. And what typically tends to happen is we over provision the number of EC2 instances. And as such, we probably like operating at a higher cost for a particular scale test session. And this is something we want to address as part of our new environment. The second tool, as I mentioned, and here I'd like to shout out to the test RTC folks here. It's a great asset for us, I must say, and we have and continue to use it to conduct various kinds of tests, mainly dealing with our web SDK. So dealing with browser compatibility, simulcast capabilities, and also being in a position to vary network conditions and run these SDKs under those network conditions. However, there are many aspects that are obviously specific to Dolby.io, and as such, we're not able to cover those aspects using the test RTC tool. Furthermore, we have to say that the cost factor plays a role here. We are limited in the number of sessions we can run. So given all these factors, we decided to push ahead and build an in-house solution that essentially makes use of open source technologies and cutting edge auto scaling, infrastructure provisioning features, and base it on a loosely coupled publish subscribe architecture pattern. And we believe this approach will help us meet our scale testing needs. And with that, we can dive deeper into this architecture in the next chapter. So here I will dive deeper into the architectural diagram and walk you through some maybe core components of the architecture, which is essential to understand why we took that and where we believe that helps us. So without much further ado, let's dive into a heavy slide. This is the architecture slide. So this is a bird's eye view of our newly set up scale test environment architecture. This has been running for about 4 weeks now. On a very high level, it's built on a Kubernetes cluster, as I mentioned earlier. It uses AWS Carpenter under the hood for horizontal scaling. It uses Redis as a component to enable us to build out this loosely coupled architecture that's based on the publish subscribe pattern. And here I'll talk a little deeper into the individual components. But just to set the stage up front, one thing was we needed to significantly improve the usability of the environment so that we reduce the hurdle for any engineer within the team to actually run a test. That was one significant factor. Secondly, we needed to have the capability of bringing in new clients into the mix. And what I mean by clients is actually the actual web SDKs, C++ SDKs, or even thin clients. So thin clients, so we have a mix of real and thin clients. And the reason for this is we want to be able to build realistic end-to-end scenarios as well as use, for example, thin clients. These are basically resource constrained clients that are mainly used to generate traffic onto the platform. Thirdly, the clients needed to be more or less stateless. And what I mean by more or less stateless, I'll get to in the subsequent slides. But yeah, they needed to basically get a blueprint of what they needed to do without having too many dependencies or even strict dependencies to the rest of the system. And typically, for an end user, we leave the choice of which client to use up to them when they're specifying that within that blueprint that they submit to the system. But we're also working on approaches where we can, tell clients that, they can tell the environment to optimize on a certain parameter. For example, optimize on cost or optimize on a mix of different clients. So we can mix and match to meet certain criteria. So overall, the workflow of this cluster is roughly divided into 8 stages today. On a very simple level, a customer or an end user simply submits a config to the system. That happens in stage 1. All they do is do a post to an endpoint, and from that point on, the rest of the cluster actually takes care of the whole thing, and they don't need to worry about anything else. Don't need to worry about EC2 instances, any kind of infrastructure, nothing. From that point on, the rest of the components essentially take care of running. So component 2 and 3 ensures that you have one job running at a time. Obviously, this is flexible. For now, we've kept the queuing aspect there to ensure that only one job runs on the cluster. This is mainly there to ensure that, at the moment, we do not want multiple jobs running in parallel. because we have seen certain overlapping and two jobs sort of interfering with each other. So that's something we want to avoid and working on to improve. So once a job comes in, the main focus then happens by the job runner, and sections like 4, 5, 6, 7, and 8. So this holistically builds up that publish subscribe architecture model. Here, the job runner basically creates, he knows from the config how many clients it needs to spin up. It spins up a set of job specs. So these are typical Kubernetes job specs. These spin up the clients basically. And these clients, once they come up and ready, they're actually listening to Redis on a certain topic that's specified by the job runner. And once they signal to the job runner that they're all up and waiting for the message, the job runner basically fires that blueprint out. And all these jobs that are listening on that topic receive that blueprint, basically go ahead, execute on it, and then they're basically done. So this is on a very high level, the workflow, or at least the core workflow that's part of this architecture. There are other aspects where the publish subscribe system enables us to do additional things in the future. So we obviously want to have reporting, analysis, and monitoring aspects for a given session. So the publish subscribe model enables us to basically plug that in. One point I want to add here is regarding resources. So when we run smaller tests, we typically tend to use spot instances, and this has tended to work pretty well for us. And for much larger tests, where we go above 1,000 and or into the 5,000, 10,000s and all that, we would have to go with on-demand instances. But of course, this comes, as I was saying, this comes with its caveats, and I'll talk about that in the next slide. So I just want to highlight, why did we choose a DSL? We purposely decided to go ahead with the DSL approach. The DSL is basically a simple YAML-based syntax, and it's used to describe the scenario an engineer would like to run. Additionally, it gives us the capability of being declarative. So it's a declarative model, and once a configuration is submitted, the load cluster basically executes this for the test engineer. There are no hidden things inside there. Everything is specified within this YAML, and this is what you get executed. There are a few reasons we went with the DSL approach. The approach enables us to separate the different types of clients we can use within the environment from the actual scenario definitions. It allows test engineers to concentrate on designing solid scale test scenarios to be able to focus on that, while engineers developing the tool and in the back end, they have the capabilities and the flexibility to bring in different client implementations as long as these two worlds adhere to this contract that's specified in this DSL. Secondly, it also offers a lesser of a hurdle to ramp up on for test engineers or generally even other engineers. At least that is what has been our observation as we've tried to run various scale test scenarios. Everything has some time to ramp up on, and we believe that this approach has the least amount of time. So it's a simplified DSL language to specify the scale test scenario you want to run. And lastly, it keeps us flexible as we make changes to the environment. And so we decided to go with this approach. And it has proven to be really good so far. Obviously, there are caveats here, but I think this is something that we are working on. As we move into the other parts of this architecture, the two other significant parts are the publish subscribe model and these heterogeneous clients. As I mentioned, often in the rest of the presentation, we needed to build a loosely coupled architecture. And the publish subscribe pattern is what we adopted in order to build this loosely coupled architecture. And for that, like I mentioned before in the architecture, we have used Redis as a component, as an implementation essentially of that pattern. Obviously, this loosely coupled architecture, it sounds good, but there are, like I mentioned, there are some caveats. When clients essentially get a blueprint through these messages that flow, that are like published and the client subscribe to, they're good as long as, the infrastructure and all these pods and everything work well. They're actually perfect. Now, imagine some of your clients' pods that are running die and they come back up. Now they're suddenly skewed from a timeline perspective compared to the rest of the clients that are running within your test scenario. And this brings the entire test scenario completely in confusion. So this is definitely one of the caveats we have. We do not know of any specific approach, right? Just yet to be able to like fix that. But we're looking at that right now. And yeah, so in that sense, these are not strictly stateless. We would have liked them to be strictly stateless, but this is something we'll have to live with for now. So to summarize, so I spoke about what our aims are in terms of improving the platform's capacity. So we aim to hit 1 million listeners, and we aim to actually be able to stream out up to 25 presenters to all the listeners that are within the conference. And that's by doing, intelligent video forwarding techniques and things like that. Secondly, we looked at various kinds of KPIs that we address as part of our load and scale testing scenarios. Our aim is to build a platform to build a holistic picture of all of that brought together. So, you can correlate clients in the back end and to the actual scenario that is run. This has been one of the biggest pain points right now is correlating all the different stuff that happens. And the publish subscribe architecture that we then looked at in the last section helps us to actually bring all of that together as we're able to now plug in reporting capabilities, monitoring capabilities, and analysis capabilities for a particular session that is then run. So with that, I'd like to say thank you for giving me the time here. And yeah, I'm open to any questions you might have. Thank you.